In this tutorial, we will be discussing molecular polarity. So why are some molecules polar and others aren't? Well, you have to look at the bonding and the three-dimensional structure of the geometry. Polarity affects the intermolecular forces of the attraction, such as boiling point and solubilities, and you might remember the phrase, like dissolves like. Polar substances dissolve in polar substances, while nonpolar substances dissolve in nonpolar substances. Non-bonding pairs affect the molecular polarity. They pull the electron density strongly, so it creates an area that's more electrodense. In order for molecules to be polar, they need to have a polar covalent bond within the molecule, which is the difference between the atom's electronegativity. A net dipole moment is what occurs when there's an uneven amount of polarity. Molecules' electron geometry is not symmetric. Symmetric molecules do not have dipole moments. They're considered nonpolar, while unsymmetric molecules do have dipole moments, and the molecule is polar. I'll give you some examples. If we have an atom here, let's say boron, and you have only one fluorine on both sides. Both fluorines are pulling at the exact same amount, so they end up canceling each other out to have a nonpolar compound. However, if you have a situation where, like water for instance, where it's a pent formation, the difference in polarity here actually ends up having a polar output. And notice that this bond angle is different than 180 degrees, so they cannot cancel out then. If it's BF3, it's considered nonpolar because all the fluorines, once again, are pulling at the exact same amount. However, for tetrahedral, the dipole moments of 4 identical polar bonds will cancel. The molecules are nonpolar. But if you have a lone pair situated here, the dipole moments of the 3 polar bonds of a trigonal pyramidal arrangement will not cancel. The resultant dipole moment vector is shown in red. The molecule is then polar. So you have to look at whether or not the polarity is being canceled out by one another. So let's look at CO2 versus H2O. CO2 is a linear arrangement. Even though oxygen is more electronegative than carbon, so we have the polar bonds going in either direction, they're canceling each other out to have no net dipole moment. There's no polarity altogether if you add those two things together. Whereas if we look at water, the oxygen is more electronegative, so the electrons are drifting towards them, plus you have lone pairs here. Because they're not able to cancel each other out, it creates a dipole moment, meaning it's a polar molecule. You have an electron-rich area up here. Molecular polarity explains solubility of substances like dissolves like. Oil is nonpolar, while water is polar. What's happening is when there's water, you have a partially negative and partially positive end, like we just showed. Well, this partially positive end is then attracted to another partially negative, and so on and so forth, and it keeps going and going and going. It's that attraction that makes it dissolve. However, if there's a nonpolar substance here, there is no positives and negatives for it to be attracted to. So therefore, it doesn't mix together. Molecular polarity also provides information on the chemical and physical properties such as melting and boiling points. Notice with water, its boiling point is 100 degrees, while CH4, a nonpolar substance, is far lower. That's because the molecular interactions involved in a polar molecule are holding it together more, and they don't want to interrupt that pattern. Whereas CH4 doesn't have as many molecular interactions, and therefore it does not hold together as easily. And that explains how to determine if something is polar or not.